Welcome to the Crazy Hat Chemist. So here we are in stoichiometry and dimensional analysis, and number 7 subset of videos is empirical and molecular formula calculation. So here we go. Bam! So empirical and molecular formulas, a little bit of definition revisiting, and of empirical formulas are the following. It's the simplest or smallest whole number mole ratio. We're not going to round until the end of these problems. You can either add or subtract a tenth to get a 0 in the 10th position. And we've already gone over that already before. We've done 2 examples at least. The molecular formula is a whole number multiple of the empirical formula. So here's an example. CH2O. That's an empirical formula because this cannot be reduced. And this is actually methanol or formaldehyde. If we multiply this by 1, we get the same formula, which is now an empirical formula and a molecular formula. So it's an empirical formula and a molecular formula. However, we can multiply it by any whole number. And if we multiply it by 2, by 3, by 4, by 5, by 6, if we multiply it by 6, we get C6H12O6, which we know that as glucose. We can multiply it by any number we want to, any whole number. So there's an infinite number of molecular formulas of a single empirical formula. The same rules here apply to molecular formula and empirical formula for rounding. I need to get a whole number. So here we go. Let's do a problem. Boom. Okay. Calculate the molecular formula of if the molar mass is 482 grams per mole and the compound contains 29.0% sodium, 40.5% sulfur, and the remaining mass of oxygen. So first of all, the 482 grams per mole, that's the molar mass of the molecular formula. I first need to solve for the empirical formula, then I can solve for the molecular formula. So the first thing I need to do is I need to sum up the sodium's percentage, the sulfur's percentage, and then I have 100% of my compound. So 100 minus the sum of sodium and sulfur, and that will give me my mass of oxygen. Okay? Hopefully that makes sense to you. I am solving for X, Y, and Z here, just like before. So, and then I'm going to solve for that N value, which is my molecular formula. So I'll come back to that. Here is solving for the percent of oxygen, which we know is, since we have 100%, we're assuming 100%, that means I have 100 grams of compound. And so this is now 30.5 grams of oxygen. So I have 29.0 grams of sodium, 40.5 grams of sulfur, and 30.5 grams of oxygen. I'm going to convert all 3 of these into moles of those same elements, respectively, using their molar mass. I want you to pause the video and do that yourself. Bam! Okay? Then what we're going to do is we're going to get these values. These values are right here. We're going to look at all these values and find the smallest number of all 3, and then we're going to divide all of them by that same small number. Remember, the empirical formula is the simplest whole number mole ratio. That drives the math. I need to get moles, and then I need to get a ratio of moles, so I'm going to divide all of them by a ratio of the smallest number. You should see that the sodium is the one that we're dividing all of them by. So that one will actually be a 1 exactly, with no decimal places. So here's what I get with those. Now, the 1 for the sodium is perfectly fine. The 1.0 for the sulfur is perfectly fine. So the mole ratio between the sodium and the sulfur is 1 and 1, so I'm good with that. But the oxygen is a 1.5. Now, I cannot either add or subtract 0.1 to 5 to get a 0 in that position. So this is what we're going to do. Okay? So you should see that that's right there. So we need to multiply by the reciprocal of the 0.5. What's the reciprocal of 0.5? 2. So we're going to multiply the oxygen's mole ratio by 2. We're going to keep that same mole ratio the same with the sulfur and the sodium as well. So 2 times 1 is 2. 2 times 1 is 2. 2 times 1.5 is 3. And now I have my mole ratio value. So now I can substitute the 2 in for X, the other 2 in for Y, the 3 in for Z, and now I get my empirical formula. You should see that I cannot reduce the 2, and the 3. And you should also know the name of this. This is sodium thiosulfate. Okay? All right. Now, Now we have the empirical formula. Now we need to get the molecular formula. So it is a whole number multiple of this. So the empirical formula and the molecular formula can be the same, but they might not be. So here we go. Here's what we're going to do. We're going to solve for n. Okay? So this is all about the n, and it's molecular over empirical. So if you think about it this way, it's all about me. Me. That's M over E. That's the me. And it's the molecular over the empirical. And what are we going to replace the molecular and empirical with? They're molar masses. So we're going to solve for the molar mass of sodium thiosulfate, and you're going to plug that into the denominator. You already have the molar mass for the molecular formula. You're going to plug that into the numerator. Your grams per mole in the numerator and denominator, they cancel, and these are the molar masses for those right there. The 482 was given, the 158.017 was solved for by you, hopefully. And this is our whole number right here, and we're going to substitute this whole number in for n. And then we're going to distribute that 3 over everything inside that white parentheses there, and then we're going to get this formula right here. I don't know the name of that, but you can reduce this to an empirical formula. You can reduce that to the empirical formula, the Na2S2O3. And it is a molecular formula, so it is a whole number multiple. Okay? Hopefully that problem worked out super well for you. That was an empirical and molecular formula calculation. I can't wait. The next time we're going to be doing stoichiometry with balanced equations. So hold on to your periodic tables, and I'll see you next time.